Tendría 53. El de Caracas, que figura no, pequeño. Pero igual, me había dicho el doctor Silva que preguntáramos si alguna persona del presente debe irse en el transporte del Teque, Charalá, Victoria.
Bien, muy buenas tardes a todos los presentes y participantes del Nano Simposio IVIC 2023. Ya los invitamos a tomar asiento para dar continuación de nuestra jornada vespertina. Igualmente saludamos a las personas que están conectadas a esta hora en nuestra sala de Jitsi. Les damos la más cordial bienvenida. Recuerden mantener sus micrófonos silenciados para poder iniciar con la siguiente presentación.
Aquí está compartiendo, no lo puedo. Estamos compartiendo en YouTube. Sí, ya. No es eso. No. Tienes que abrir un poco de... ¿No está aquí? Un PDF. Un simposio. Abre esa. ¿Dónde está? Está en el PDF. ¿Pero dónde? ¿Qué? Esto para ponerlo ahí, o sea, para que no se vea mi interfaz. En la página, en la carpeta que se pone así.
No estaba Fernando.
Bien, damas y caballeros, continuamos con nuestro ciclo de ponencias. Para nosotros, para el Instituto Venezolano de Investigaciones Científicas, el IVIC, le da también la más cordial bienvenida y el placer de presentar a su siguiente ponente de talla internacional que nos acompaña en este importante evento. Se trata del doctor Bernard Helen. Él es investigador y profesor del Departamento de Física de la Universidad de Montpellier en Francia desde el año 1996. Profesor de la Universidad de Montpellier desde el 2004, responsable del Glass Physics Group en el laboratorio Charles Coulomb de Montpellier, de la Universidad de Montpellier, miembro del comité directivo y del consejo de la International Commission on Glass, una organización que reúne a actores académicos e industriales de todo el mundo en el campo de la ciencia y la tecnología del vidrio, responsable de una maestría en física de la materia condensada y luego nanofísica en la Universidad de Montpellier entre el 2004 y el 2015. Dentro de su actividad científica, tiene la experticia en el estudio de las propiedades estructurales y vibratorias de los sistemas desordenados, vidrios, ferroeléctricos, materiales, y recientemente amplió su actividad a simulaciones de dinámica molecular en física de materia condensada y biomoléculas. En biometría tiene 65 artículos en revistas de alto impacto y 6 capítulos en libros 59 comunicaciones orales, incluyendo 20 en invitaciones. Recibamos con un fuerte aplauso al doctor Bernard Gelé para la siguiente ponencia.
Which one?
Y el apuntador, hay que identificar el apuntador, el apuntador.
Okay.
El láser, el rojo.
Yes.
All right.
Okay. All. So thank you everyone. Thank you organizer for this wonderful day. I'm sorry. So that's the first time I come in Venezuela, and I always enjoy my stay there. So I hope it's not the last one. So thank you very much for the invitation to give this talk today. As you said, Chairman, my main activity is mostly devoted on glasses and on ferroelectric materials from the point of view of the phase transition. So I'm not completely in the field of nanoscience, but so I found in my activity something which is related to nanoscience, and hopefully which could interest you as an audience. So I will speak today about ferroelectric materials, nanostructures, and why these materials is because they exhibit giant dielectric properties, which can be very useful for technological application, and are useful. I mean, there are many use of these materials in industries. Sorry. So this work has been started by Alien Alzheim, which was a PhD of mine, and continued by Mariam Al-Sabak, another PhD. And it is a collaboration with people at the École Centrale in Paris, and also people at the large facility in France, neutron source and X-ray synchrotron source in Grenoble. So first I will introduce the materials. So the material I will be talking about today are oxide perovskites. Oxide perovskite has a wide family of materials with general formula AbO3. And most of these materials exhibit ferroelectric character. And so the general structure of these compounds is cubic with an octahedra here made by oxygen atom. And at the center of the octahedra, you have the B site, which in the case of strontium titanate, SrTiO3, is the titanium here. So strontium titanate is a perovskite material, which is very, very well known, by the way. It has been a prototypical material for studying the phase transitions in the 70s and 80s, so that's a long time ago. And but it exhibits very interesting properties, such as giant dielectric one, I think. Oh, no, I'm sorry. You should run my PPT, not my PDF. PPT, yes. Because otherwise, yes. Great. Okay. Perfect. That's better. Thank you very much. Okay, so strontium titanate, as I told you, is a perfect crystalline structure. It is a very well-known perovskite material, it is ferroelectric, but it is a simple form of the ferroelectric materials. You have complex ferroelectrics here, which exhibit exactly the same structure as strontium titanate, but then in that systems, the central site, the B site, can be taken by two different atoms, B prime or B second, and this make what we call solid solution with the B site, for example, in this sample here, the B site made of magnesium and iridium here. And this makes solid solutions, and the properties are due to the chemical, positional, and also charge disorder of the system. But today, I will just focus, all of these materials exhibit giant dielectric properties, but today I will focus on strontium titanate, which is the simplest form of this kind of materials. Okay, so a bit of history of this compound. So strontium titanate exhibits a structural transition at the temperature of 105 Kelvin from cubic to tetragonal. So in the tetragonal form, you have the growth of the C tetragonal axis. Okay, so the square cubic frame develop a C tetragonal axis. But in addition, if you look on the top of this structure here, you see you have the octahedra there, and the octahedra rotate in antiphase, one octahedra in one way, the other one in the other way, etc., etc. And you have an angle phi which develops at the same temperature here. And this angle phi, by the way, is the order parameter of this transition. It is 0 above the 105K and non-zero below 105K. And so you can measure these two quantities for the angle, the rotation angles of the octahedra here. You have the zero value above 105K, and below you have the development, the growth of this angle here. And you can measure this angle by many techniques, EPR, Raman, neutron scattering. There are many ways to measure this angle. And same for the lattice parameters. You are cubic at high temperature, so there is just one lattice parameter A for the cube. And then below 105K, the C-axis develops here, and you have a splitting of this A-axis, of this A lattice parameter. So that's the two structural things which develop below the transition at 105K, C-axis and an angle. So another property, which will be the property we will discuss today, is the dielectric constant, or the dielectric permittivity. As you see here, that's the temperature, and in the abscissa, and when you lower the temperature, the permittivity increase, and in strontium titanate, it can reach a value up to 40,000, which is huge for a material. As a reference, usually materials have a permittivity of 10 or 100, but to have more, it's not common. So this material have a huge dielectric constant, as well as the complex ferroelectric materials, PMN, PZT, which exhibit a permittivity of over 25,000, which is also very huge. And this is very important for application. For example, you can build capacitors with very high capacitance. And since you know capacitors, if they have very high capacitance, they can store electricity. And then you can restore electricity by unloading the capacitance. So that's one possible applications. And there are many other transductor, actuators, and also 3D memories for these samples. And also, in your car, you have many sites of your car which have such materials here. In particular, PZT, which is the most common one in the technology in cars. For example, in the light, in the brakes, in the wheel, and so on. You have many sites where you have such materials. Okay, so now this is the dielectric constant in single crystal. But usually when you use these materials, you use this as ceramics because it's easier to produce. So you use this material as ceramics, and what happens in ceramics is this. So in ceramics, if you plot here as a function of temperature the cell, the dielectric constant, and you plot that depending on the grain size of the ceramic. Here it's 1 micron, 1.5 micron, 150 nanometers, and 80 nanometers. You see that the dielectric constant decreases. So this lowers the capacity of these materials for their application. And if you look here to this graph, in abscissa you have the grain size, and here you have the permittivity, and you see that you have a strong lowering, decreasing of the dielectric constant when you reduce the grain size. So to understand this behavior, we have to go into the details of the shape of the grains in case of ferroelectric materials. In this system, you have what we call the core shell model. Due to the growing of the grains, you have two distinct regions. You have a core here, which is made of the perfect material, and you have a shell which surrounds the core sample. And the shell is not of the same material but distorted. It's distorted, and so as it is distorted, it does not have the same permittivity. And so you have a kind of composite with two materials made of exactly the same chemical elements, but one is perfect and the other one is distorted. And so you have the permittivity of the core, which is much higher than the permittivity of the shell. And what says the effective medium approximation? If you make of these grains, you build a ceramic, then for the current to go through the ceramic, you have two different ways. The one way is in the way where the current goes through the shell. So that's what we call the percolation volume of the ceramic here. And so there you just have one capacitor, which is the capacitor made of the shell. And if you go directly through the rest, you have two capacitors in series, the shell and the core. Okay. And that's a parallel circuit. And if you calculate the effective dielectric constant for this circuit, you find this formula, which is quite easy. This comes from this way, and this part comes from this way. Okay. But what measure when you are measuring the dielectric constant by usual electrical measurements, what you are measuring epsilon effective. You don't separate both components of the dielectric constant. So is it possible to access separately epsilon of the core and epsilon of the shell? That's the question. And yes, it is. And to do that, we applied optical spectroscopies. So, if you look at the vibrations of the system, you have one vibration which is very important, which is a polar vibration, a soft polar vibration. Here, you see, in the cage, the central atom moves up and the octaedra moves down. Okay, this makes a vibration like this, and this is what we call a polar vibration, because it carries a dipole moment. And so, this mode here, you can measure it. For example, here, it has been measured. This is by Hyper-Raman, but I will go to that after. As a function of temperature, you measure the frequency of this motion, and you've got something which is decreasing very fast with temperature, and which goes to very, very low frequency. And this is what it is. This is just to schematize this. Okay, it's simpler not to make the oxygen atom moving. So at high temperature, the atoms are moving fast, the frequency is high, and when you lower the temperature, the atoms are moving slowly, and this is what we call a soft mode. And what is very interesting here is that the frequency of this mode is directly related to the dielectric constant by a very simple formula, which is this. So if you plot the inverse of the square of this mode with temperature, you are able to find epsilon. Easy, very easy. So and this is the epsilon I've shown you just before. So this quantity here is exactly the reverse of that square. Okay, that's the dielectric constant as a function of temperature. Okay, so that's very easy by optical spectroscopy to access a physical quantity such as the dielectric permittivity. Okay, so what kind of optical spectroscopy can we use to do this job, to measure the frequency of this soft mode? So if you look at the light scattering, the light scattering is a Fourier transform of the correlation function of the polarization P of the material. And the polarization P can expand in terms of the dipoles. Mu is the permanent dipole, and this gives you the infrared activity. And at the first order, the induced dipole, alpha times E, gives the Raman intensity, and then the Raman is a two-photon process, where one photon scattered, one incident photon scattered one photon after interaction with a vibration in the media. And this vibration here will be our soft photon mode. But if you continue this expansion here, at second order, here, you have what we call hyper-Raman scattering. That's hyper-Raman is the first term, the first nonlinear term. And so hyper-Raman is a nonlinear spectroscopy where you need two incident photons to scatter one photon after interaction with the vibration. And the interest of hyper-Raman is that it does not have the same selection rules as Raman. You see different mode than the mode you see in Raman. For example, if you take the cubic structure of tungsten titanate, you see that you have the polar modes F1U. The three polar modes are active in infrared and hyper-Raman. And there is another one, F2U, which is only active in hyper. But you see, since tungsten titanate is cubic, there's no mode active in Raman. So if I want to follow this polar mode, the mode which makes this motion of the central atom moving up and down, I can't use Raman scattering. So the way to do that is to use hyper-Raman scattering. But there are limitations in hyper-Raman scattering. For example, the process is 1 million times weaker than in Raman. So if you have to stay 1 minute to make a Raman spectra, you have to spend years to make a hyper-Raman spectra. So one idea is to use high power laser and high diffractive optics to compensate this lack of intensity. And so 15 years ago, we constructed an apparatus in Montpellier, an hyper-Raman setup in Montpellier. And just to give you some details, you use a pulsed YAG laser, because then you have very high power pulse at disposal to make your scattering. And then you irradiate your sample with an IR beam, infrared beam, and you look at the scattered beam in the grid. You irradiate in the infrared and you look in the grid. Okay, there are different setups here, but after in this arm here is similar as in Raman, somehow. Okay, so for this study, we had at disposal one commercial nanopowder of 50 nanometers, and we use this nanopowder was sintered by plasma sintering, sorry, and we got two samples with finite grains of 80 nanometers and 150 nanometers. So we have two samples at disposal to do our study. So if you look at the Raman spectra, the polar modes are inactive in Raman in the cubic phase, as I told you, But remember, in Central Titanic, you have a transition from cubic to tetragonal at one moment of time. So the polar mode now are active in someone has switched on his. Yeah. So the mode are active in Raman in the tetragonal phase. But if you look at the Raman spectra here, this mode, which we are looking at, is this bump here, this bump here, this bump here. It is very, very weak, and it is embedded into a very strong backbone signal. So that's not very useful. I mean, Raman is not a useful technique to measure this mode. So we can use infrared absorption. But the problem with infrared absorption here is that you probe the sample at a wavelength which is much higher than the grain size. And so what you see is an effective medium. You don't see the details of the grain because you probe your sample with a wavelength which is much higher than the grain size. Okay, so this will not help to see the core on the grain, on the shell. So infrared you can forget. And so the only remaining spectroscopy is hyper-Raman, because here the wavelength is about 1 micron, which is comparable to the grain size of the grain, to the size of the grain. And so now, if I compare what we have in the spectra we have in Raman, I mean hyper-Raman, this is it. So here I reproduce exactly the same spectra as on the slide before, with this small mode here, with this small bump which corresponds to the mode of interest. And here is the hyper-Raman spectra. You see, it has no background tone, the mode is very strong, and you see that this mode here corresponds to the tier 1 of the Raman, and this tags here correspond to what has been associated to X mode in Raman here. So we have, this is the tier 1, this is the polar mode we are looking for. And now, the question is why it is a doublet. And this is simple. It is a doublet because we have both contributions, one for the grain, one for the core, and one for the shell. So this component here corresponds to the signal in the core, and this corresponds to the signal in the shell. So the frequency of this mode directly relates to the permittivity. The frequency here and the frequency there correspond directly to the permittivity, and the band area corresponds to the volume fraction of core and shell. So we have many information in the spectra concerning the dielectric properties. So we made the temperature measurement here. So you see the decrease in frequency of the mode with temperature in the core in the shell, and in the two ceramics we had at disposal. And so we can plot now the frequencies here. So that's the frequency of the mode as a function of temperature for the core and for the shell here. And in blue for the large grain ceramics, and in red for the small grain ceramics. And what you see is that for the large grain and for the small grain, the temperature dependence are exactly the same. And so why, if the temperature dependence of the permittivity in both core and shell are the same, why the effective dielectric response decreases when you reduce the grain size. So first, before answering this question, since we have the frequency, we can access the permittivity in both parts of the sample just by using this formula here. By the way, in the literature, this constant is 26.3, and we can get it experimentally from 26.8, which is very, 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 very close. And this is it. So now we have the permittivity just corresponds to the amount. So if you calculate the ratio between the intensity of the small grain to the large grain size, you end up with this, which is a constant 1.87 times the thickness of the shell for the ceramics with 80 nanometers grain size over the thickness of the shell of the large grain size ceramic. And so, if you plot this, now if you plot as a function of temperature the intensity of the shell, you see that if you multiply the intensity of the shell of the small grain size ceramic by 1.5, you find exactly the same as for the large grain ceramics. So I don't want to go into detail of this, it's really easy to understand, but this says that you have exactly the same temperature dependence in both ceramics of the shell size, shell thickness. So that means that the shell thickness in both ceramics are exactly the same. So the difference in effective permittivity just comes from the ratio of core and shell in the ceramics, not more than that. Okay, so we have many information. We have the ratio of core, of the volume of the core, we have the volume of shell, we have the permittivity of the core, the permittivity of the shell, and now what we want is to reproduce the effective permittivity measured experimentally by electric measurements, this one. So what we did a simultaneous fit of these two curves with the data we have, and we tried 3 models. The 2-layer models I've shown you at the beginning. One average model here I will not discuss about, and the third one. And so these 2 models do not work. I will not tell you why, but it doesn't work. And so to account for this behavior here, we need a 3-layer models which involve a core grain, a shell, and a dead layer at the surface. So that's a 3-layer model. And if you do that, the effective permittivity is given by this formula. This is quite a heavy formula, but here we know many things by experiment. And so in this formula, there are only 3 independent parameters. The permittivity of the dead layer, the thickness of the dead layer, and the thickness of the shell at room temperature. That's the only parameters 3. All the other parameters are given by the experiment. And if you do that, you find this blue curve, this blue dashed line here, which is not bad. So with only 3 parameters with the data. And if you free this parameter, which is the constant of the relation between the electric and frequency of the mode, if you leave this free, it moves from 26 to 22, and you see you have the red curve, which is almost perfectly matched with the experiment. Okay, so we know now that the ceramics is done by a 2-layer system, a core plus 2 layers. 1 core, 1 shell, and 1 dead layer. The dead layer, the shell here, the radius of the shell increases when the temperature decreases, like this. When the temperature decreases, the shell thickness increases. And by the fitting, you have all the information of the core and shell. We have the permittivity of the core, we have the permittivity of the shell, we have the thickness of the shell from 1 to 3 nanometers, and we have the permittivity of the dead layer and the thickness of the dead layer. So we have all this information, all included in our optical spectroscopic measurements. Okay, to summarize on this part, to summarize here, it is possible using hyperlens scattering to reconstruct the effective dielectric constant of the grains in constant tight by using the layer model, a core grain surrounded by a shell and a dead layer. The shell thickness does not depend on the grain size. That's what we found also. And the difference in the core and shell volume fractions in the ceramics, because the shell is always the same. The thickness of the shell is always the same. So if you reduce the size, you reduce the radius of the core, and then you reduce the dielectric permittivity. That's what we found here. Now, we did that, and then we did another thing, is we grow artificial core shell structures. So what the aim of this is to make engineering of solution titanate, nano, and microparticles. So we have a reference sample, which is particles of 1 micron size, which exactly as normal which is a grain which show the electron and the bright one correspond to ZRO2 grafted as the surface of the sample. Normal, which is rich solution titanate with its core shell structure, and another one where you have grafted some ZRO2 particles on the surface, on the outer surface. And if you do diffraction on that, you see that in the artificial core shell structure, the structural transitions here develop at 160K instead of 105K, which is something quite interesting. And only in the artificial STO core shell structure, in the normal one, the structural transition develop at 105K as usual. If you plot the latest parameters here, and first, for example, the angle, you remember the rotation angles phi of the octahedra. For the reference samples, it goes down at 105. For the artificial samples, the two artificial samples, it goes down at 160. And so this, for the normal sample, you have exactly what you expect, a cubic to tetragonal transition, as I've shown you in the introduction. But here in that sample, you have a development of a third lattice parameter here, and we found that it is an orthorhombic phase. So by grafting the surface of the grain, we change the structure of the core of the grain. To know a bit more about that, what we did is what we developed the Nano theory, and we renormalized this B1, B11, and B2 parameters, which is the usual parameter for the Nano theory, by terms which are underlined in red here. So K1 corresponds to a normal stress, K2 corresponds to a shear stress, and the index NY, NX, and Z correspond to spherical particle if n equal 1, and non-spherical particle if n, x, y, z are different. So we can play now, using the Nano theory, by varying a shear stress or a normal stress on the grain, and by varying the shape of the grain, whether they are spherical or ellipsoidal. And what we found is this. First, let's take spherical grains. If you have spherical grains, and you apply a pressure Pascal on your sample, and you go into this line where the shear stress is null, lower the transition down to 145K, which is somehow what we found artificial conscience. And so now, if you apply a shear stress, you see that it goes from tetragonal, which is a normal case, to rhombic. So you have a transition here at the shear stress But remember, the phase to form is not robotic, it's orthogonal.
¿Qué vas a hacer?
So
Sales de
what we did now
sales de la
is we consider that the grains are not spherical anymore, but they are ellipsoid. Very weakly ellipsoid. You see there is 0.95. 5% ellipsoidicity along the z-axis. And if you do that, you see that you apply a shear stress here, still at 2 gigapascal of pressure, uniaxial pressure. But if you apply now a shear stress, now you induce an orthogonal phase. Exactly what you found experimentally. So this is to say that you can completely change the property of a grain depending on the stress you put on it, on the shape of the grain. So I come to my conclusion. So in the first part, I've shown you that it's possible to reconstruct the effective permittivity of a sample using inelastic vibrational spectroscopy. And here, I show you that by inducing uniaxial pressure or shear stress on samples, you can induce phase transitions which are not expected in the bulk materials and which can be helpful for new physical property eventually. Thank you for your attention. I'm open for questions and si tienes preguntas, por favor, hacéisles en español.
I have a question. In your model, you have a very sensitive spectroscopy data to propose a model for the behavior of your samples. Or the perfect core and the shells.
Yeah.
But the more direct evidence. Can one try with high resolution to the electron microscopy, at least with the 80 nano, very clear high resolution image?
It's possible. The problem is it is the same material everywhere.
Pardon?
It is the same material everywhere. You have to take that into account. You will not have much contrast.
Yes,
it is the same
I'm looking for constant, high resolution constant for diffraction constant. So I suppose you have a perfect core,
yeah.
Crystalline, very crystalline, speaking,
yeah.
Perfect. But the shell is not.
It's not. It's the same, but it's not perfectly crystalline.
So one can see
yes.
in high resolution microscopy.
Yes.
One perfect,
eventually.
And in the other,
in your model, you have grains with a core and shell, but
yes.
with joining the grain, there is empty space.
No, I mean in our system, in our samples, the density is it's more than 98% densified, so there's almost no empty space.
How do you use the EPR technique in this?
I did not do that. That's a very old APR. It has been done, by the way, by Kara Mueller. It has a Nobel Prize for something else, but it has done EPR with iron.
All right.
It's iron.
Yeah. Thank you very much. Muchas gracias al expositor.
Gracias al doctor Bernard por su presentación. Damas y caballeros, inicialmente le voy a dar la palabra al doctor Pedro Silva, quien va a dar algunas indicaciones, y posterior a ello vamos a adelantar el receso, ¿ok? Por unos 15, pero rápidos minutos, porque tenemos todavía ponencias, así que presten mucha atención y a lo que termine el doctor Pedro Silva aquí su intervención, que es breve, vamos a tomar el refrigerio.
Ok, no, quería anunciarles que al finalizar la última charla, que es la de la doctora Susana Pinto, vamos a tener unos minutos, esperemos que nos dé tiempo, para tener una especie de conversatorio sobre el reimpulso de las actividades en nanociencia y nanotecnología. Dentro de estas cosas está comentarles, bueno, por allí está el doctor Atencio, actual presidente de la red Nano. Ahí está, creo que por ahí hay un tesorero y está el fundador de la red Nano por aquí, Anor Hamid. Quisiéramos saber cuál es la perspectiva con respecto a la red Nano, un poco conversar sobre el reimpulso de la actividad de posgrado en nanotecnología que la habíamos dejado en un punto así casi, pero no terminado. Entonces, quisiera que los que estén interesados se pueden quedar. Vamos a tener un transporte a las 5:30, creo que hay algunos pocos por allí. Si no, bueno, el que no pueda, que tome los transportes del IVIC o las cosas como accesaron acá. Bien, esa es la información que quería darles.
Bien, muchísimas gracias. Entonces procedemos a tomar el refrigerio. 15 minutos a partir de este momento. A las personas que están, son las 2:50 de la tarde. A las 3:05 retornamos nuevamente a nuestra sala para poder continuar con las ponencias. Las personas que están conectadas en nuestra sala de IVIC, mantenerse en conexión, son 15 minutos y ya volvemos con el siguiente ponente.
No, pero ahora